Hello and welcome to this video for Chemistry 20. This is the review of Science 10 Chemistry Unit, where again we're building those foundational skills that you're going to need for the remainder of the Chem 20 course. So one thing we're going to start today that's obviously very important in chemistry is being able to write the formula and name elements and compounds, especially if you're writing reactions. When we write reactions, we usually write everything as equations and formulas. So it's really important that you can go especially from a name to a formula. So first of all, we're going to start with elements. So when you look at the periodic table, again, those are all your elements. And elements can exist by themselves. Now, when they're by themselves, usually the formula for them is just the symbol of the element. And then sometimes you might also see the state written after it. When we write reactions especially, we want to include the states. The states of the metals are all solid except mercury is a liquid. Your nonmetals can be solid, liquid, or gas, and that information is given on your periodic table in the little elemental box. Now, metals, again, when we just write the formula for them, there's no number written after them, or you could say there's an invisible 1 put there, okay? This means that they are monatomic. Monatomic meaning when they're in their elemental form by themselves, they exist as only one atom. And we don't show the 1 when we're writing the formula. We just write the formula as it is, okay? Now, some elements, such as some of the nonmetals and hydrogen, do not exist monotomically, meaning when they are in their element form, they actually exist as small molecules. We call these the polyatomic elements, okay? Polyatomic meaning more than one. And we can actually even be specific and use the word diatomic for 2. The elements that always exist as 2 of them, again, only when they're by themselves, not when they're bonded to other elements. There's a saying to help you remember it, and it's Haber-Finkel. Haber-Finkel. These are the elements that when, again, in their element form, meaning they're not bonded to another element, they are all 2. So hydrogen, if I tell you you have hydrogen, you would write the formula H2. And technically, it's a gas. So if you wrote the full formula with the state, it would be H2 gas. Same with oxygen, bromine, fluorine, iodine, nitrogen, and chlorine. They're all diatomic. They all have 2s when they're not bonded to another element. Now, this doesn't affect their name. I would still call this hydrogen. Sometimes you'll even hear the word gas put with it. So it's either hydrogen or hydrogen gas. Sometimes, right, it just gives the state in the name. Okay? Another way to help you memorize it is on the periodic table, they make a flagpole shape, with the exception of hydrogen kind of being off on the left-hand side top by itself. But the rest of the diatomic elements make a flagpole shape: nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. Okay? Now, there are 2 other elements that are polyatomic, but are not diatomic, meaning they don't exist as 2. They actually exist as more than 2. That's phosphorus and sulfur. Phosphorus, when it's not bonded to another element, is always P4, and sulfur, when it's not bonded to another element, is always S8. Okay? Again, when it comes to naming these things, their name is not affected by the fact that they're polyatomic. Okay? P4 would still just be called phosphorus. It's still just the element name, okay? Now, you have to memorize which elements are polyatomic and diatomic. And then if you have another element that is not a polyatomic one, then it's monatomic. And metals, other than hydrogen, which can be considered a metal, all of those are monatomic with the exception of hydrogen. And then some of the nonmetals. So Haber-Finkel, a way to remember, or the flagpole shape. Okay, so those are again elements by themselves. Now, most of the time you're not going to have an element by itself. You're going to have a compound. Now, compounds form when elements bond together. And there are two main categories of compounds: ionic compounds and molecular compounds. In this lesson, we're going to review ionic compounds. So ionic compounds are the combination of a metal with a non-metal, okay? And the metal is acting as an ion, specifically a cation, like we reviewed in the last lesson, and the non-metal or polyatomic ion would be acting as the anion. So remember, cations are positively charged ions and anions are negatively charged ions. So an ionic compound will always have the positive ion written first and the negative ion written second. Now there is, for polyatomic ions, there is one polyatomic ion that can replace a metal because it's positively charged, and that is the ammonium ion. So an ionic compound might start with either a metal or the ammonium ion, and then it'll be bonded to either a nonmetal or a negative polyatomic ion. All the other polyatomic ions are negative, such as nitrate. Nitrate is NO3 negative 1. Polyatomic ions are ions that have more than one element that make them up. Okay? So ammonium, again, was one nitrogen with 4 hydrogens, and it has an overall charge of +1. You're actually going to treat it as one whole thing when you're balancing them to write the formula for the compound. Same with nitrate. It has an overall charge of -1. The 3 is the fact that there's 3 oxygens with nitrogen that form this nitrate ion. Okay? If you have a nonmetal in your element, remember, anions, when they're just a nonmetal, are always going to end in "ide." A lot of the polyatomic ions end in "ate," A-T-E, and "ite," I-T-E. Some of them end in "ide," but the nonmetals for sure are always "ide." Okay, so that's how you know if you have the nonmetal form of an element or if you have a polyatomic ion. Now, metals. Metals can either be what we call monovalent or multivalent. Okay? Monovalent means that there's only one possible charge that element will always carry. So for example, potassium will always be +1. Beryllium will always be +2. Aluminum will always be +3. When you're looking at the periodic table, and you're looking at the elemental symbol, let me just grab, my periodic table. So when I'm looking at aluminum, for example, I have my symbol, I have my atomic number, I have my atomic mass, and then right underneath is the charge. Okay? If there's only one number written there, it's monovalent. But some elements, in the middle of the periodic table especially, some of the transition metals, like iron, if I look up iron, I see my Fe, atomic number 26, atomic mass 55.85. Under there, I see a 3+, then a comma, and a 2+. This is what multivalent means. There's more than one possible ion charge that ion can carry, depending on the environment it's in. Now, they are written in order of how common they are. So 3+ is more common than 2+, okay? But when we have a multivalent metal and we're naming them, we have to, in their name, put in brackets Roman numerals to represent what charge the ion has in that compound. So for example, if in my compound I have iron with a 3+, I'm going to call it iron in Roman numerals 3. Sorry for that horizontal line again there. Iron and then Roman numeral 3. Iron with a 2+ would be called iron in Roman numerals 2. So the Roman numeral corresponds to the ion charge. Just a review of Roman numerals. If you have a 1+, it would be I. A 2+ would be II. A 3+ would be III. 4+ is IV. 5+ is V. 6 plus is probably as high as you're going to get. That's Vi. Okay? So those again correspond to the ion charge. They're all positive because these only happen with metals. Only metals are multivalent. Okay? And when you have a multivalent metal in your compound and you're naming the compound, you have to say in the name what charge it carries. Okay, so polyatomic ions, as I mentioned, are ions that have more than one element that make it up. So let's say, for example, I have the compound calcium hydroxide. Calcium hydroxide. Okay, so calcium being my metal, and hydroxide is actually a polyatomic ion. If I look them up on the periodic table, since this is an ionic compound, and again, I know it's ionic because it's starting with a metal, that means I have to look up the ion charges as well when I'm trying to figure out the formula that it's going to make up. So calcium as an ion has a 2 plus, and hydroxide is the polyatomic ion of oxygen and hydrogen, and it has a -1 charge overall. Now we'll get up to this a little bit more in the notes later on, but when we're writing the formula for a compound, our ion charges have to balance. So if I have a 2 plus from my metal, I need 2 negatives from my anions. Okay? If each anion is -1, I'm going to need 2 hydroxide ions so that it adds up to 2 negative to match with the 2 positive that the calcium had. Now, when I write the formula for the compound, I don't show the charges. This is just my background work or what I'm thinking in my head. When I write the formula, the charges are not written, but I do need to show how many of those ions it takes to make up that compound. So there's only 1 calcium needed, but I need 2 hydroxides. Because hydroxide is a polyatomic ion, I need to put it in brackets. Okay? So normally when we write the formulas, we don't use brackets. But if I have a polyatomic ion like hydroxide, and there's more than one of them, here I have 1, 2 of them, I put them in brackets with a 2 after, showing that there is 2 of these ions. Now, if you're looking at the elements specifically, this means you have 2 oxygens and 2 hydrogens. Everything in the brackets goes with that number, right? And when we draw it out here, we see there's 2 oxygens and 2 hydrogens. That's why you have to put it in brackets. If you forgot the brackets, and it looks like that, that would mean there's only 2 H's, but we also have 2 O's. So that's why brackets are needed, okay, for polyatomic ions if there's more than one. Now, what are some properties of molecular compounds? First of all, if they dissolve in water, and in order to dissolve in water, that means they're soluble, and there is a chart on your periodic table that determines the solubility of compounds that we'll review later. If you have a compound that is soluble, it will conduct electricity. The reason it conducts electricity is because the cation and the anion break apart as free ions, and then those free ions flowing through the water or whatever they're dissolved in is going to carry electrical current. When they dissolve in water, they're either going to form a neutral solution or a basic solution. Notice here how it says to know your litmus paper tests. So remember, litmus paper comes in 2 different colors. It comes in both red and blue. Now, funny thing, the red actually looks pink and the blue actually looks purple, but that's what we call it, red and blue. If you have a neutral solution, each indicator paper is going to stay its original color. So the red paper will stay red and the blue paper will stay blue. If, however, you have a base, your solution is slightly basic or very basic, it's going to turn the red paper blue and the blue paper will stay blue. So if they're both blue, think of B for blue, B for base, then it's going to be a basic solution. Okay, now how do you identify a basic solution from the formula? If you have a metal bonded to hydroxide, just like the calcium hydroxide I showed you before, whenever the hydroxide ion is present in a solution, it is going to make the solution basic. And there is a unit in Chem 20 we're going to talk about for acids and bases. But for now, just know that an ionic compound will always be either neutral or basic. Okay? Now, acids, if we look at the results on litmus paper, the red stays red and the blue turns red. So that's how you can identify something as an acid. And today we are going to review acids and, sorry, not today, the next lesson we'll review acids and how to tell if it's an acid and their formulas. Another property of ionic compounds is when they are not in water, when they're in their natural state, they are always solid. Okay, always. Any ionic compound is going to be solid. Like I said, when I put it in water, it might dissolve and become aqueous. That means it's dissolved. But before we put them in water, in their natural state, ionic compounds are all solid. Now, there's one other little thing to add here, and that is if an ionic compound is hydrated. An ionic compounds can be hydrated, meaning water is actually chemically bonded in their structure. This doesn't mean it's dissolved in water. This means water is actually part of the chemical structure. And these compounds are actually still solid. Okay? So I could have a compound. This is a compound you're going to use. Actually, it's going to come up in some of the examples, so I don't want to use that one. But let's say I had sodium chloride, then there's a dot, and then let's say a number, and then H2O. This is still a solid ionic compound, okay? But it's hydrated. So what you'll notice is there's a dot, and then a number, and then H2O written after it. When we name these, we're going to use our molecular prefixes only for the hydrate part, okay? And the water, again, is called hydrate. So the name of this compound would be sodium chloride. Again, my chlorine becomes chloride when it's an anion. And then a separate word would be decahydrate. The deca for 10 and the hydrate being the water. So sodium chloride decahydrate would be the full name of that ionic compound, that hydrated ionic compound. Okay? The molecular prefixes are on the front of your periodic table for Chem 20. Just to review them quickly, 1 is mono, 2 is di, 3 is tri, 4 is tetra, 5 is penta, 6 is hexa, 7 is hepta, 8 is octa, 9 is nona, and 10 is deca. So when you're writing the name of a compound like I just did in that example there, you're going to name the first ion. If the metal is multivalent, remember you're going to use Roman numerals in brackets after the metal. And then you name the second ion. If it's a nonmetal, again, it ends in "ide." If it's a polyatomic ion, you find it on the periodic table and give it the exact name it has on the periodic table. Then again, if it's hydrated, you add that prefix and hydrate with it. So not all ionic compounds will be hydrated. Here, our third example is hydrated, but the other two aren't. So let's start with the other two. So my first one here, I have aluminum, and actually, on your periodic table, it's actually spelled aluminium. Aluminium. I commonly use the word aluminum, but technically it should be aluminium. And aluminum is monovalent, meaning it's always 3+. There's no other charge it can have, so I don't need to use Roman numerals. And then I just name the second element, which is chlorine, as an ion because this is an ionic compound. So it's aluminum chloride. Notice I'm not using prefixes here. I'm not saying trichloride. Notice how I'm also using small letters. I'm not using capitals. When you're naming, you don't use capitals. Okay? So the name for AlCl3 is just aluminum chloride. Okay? The next one, my metal, is iron, and iron is multivalent. Okay? So I'm going to need to put numbers in there, Roman numerals. I'm going to, though, name my second element first, which is oxide. So it's iron something oxide. Okay? Now, how do I figure out what ion charge the iron has? I do a little bit of backwards math. I know that in this compound there are 2 iron ions. Okay? And I know there are 3 oxide ions. So I'm going to draw my oxides, or my oxygen, 3 times. And I know that each oxygen has a charge of 2 negative. Remember, group 16 ions are all -2. So in total, with my 3 oxide ions, this adds up to -6. Ionic compounds are always balanced, so that means I must have a total of +6 from the 2 irons. Now, if they have to add up to +6, there's 2 of them, they must each therefore be +3. So the name would be iron 3 in Roman numerals oxide. Okay? Now, some people talk about cross-multiplying, or not cross-multiplying, but crossing the charges. Sometimes that works, sometimes it doesn't. In Chem 20, you should really not be using simplified methods like that. You should really understand, again, what the numbers are coming from. And again, the fact that you have 2 irons and 3 oxygens and how their net charges have to add up to each other. Okay? The next one is another iron, but this time in the compound, there's just 1 iron. So I again need to figure out what charge it has because iron is multivalent. It is bonded to NO3. NO3 is called nitrate. Nitrate. And there are 3 nitrates. Each nitrate has 3 oxygens, but the overall charge of each nitrate is -1. Okay, so in total, I have -1, -2, -3. I have 3 negative charges that one of my irons is balancing with. So it must contain that entire 3+ charge to balance with 3 nitrates. So this would be iron 3 nitrate. And then I have to add non-hydrate at the end, because it is hydrated with 9 water molecules, and 9 is nona. Okay, so iron 3 nitrate non-hydrate. Now there are some for you to try, so you can pause this video and give these a try. So if we look at them, my first one would just be zinc phosphide. Zinc is not multivalent, so it does not need Roman numerals. And phosphorus as an anion is called phosphide. The next one would be sodium nitrate. Again, sodium is not multivalent, so it does not need Roman numerals. The next one, however, nickel is multivalent, so we do need Roman numerals. And because 1 nickel is bonding with 3 fluorides, and each fluoride is -1, the nickel must have a charge of +3. So it's nickel 3 fluoride. Now number 4, this is one of the ones where the cross-multiplying or the crisscross method would not work. Okay? The Mn, there's 1 Mn bonded to 2 O's. Each O is -2. So in total, I have -4, which means I need +4 on my Mn. There's only 1 Mn. If there was 2, I would divide it by 2 and they'd each be +2, but there's only 1, so it carries the entire 4+ charge. So this is not magnesium, this is manganese 4 oxide. Okay? The next one is again multivalent. Each sulfate is -2, and there's 3 of them, so that adds up to -6, which means I need +6 from my chromiums, but there's already 2 of them. So each of them is going to be +3. So that 3 times 2 will equal +6 to match the -6. So it'll be chromium 3 sulfate. Okay. The next one is hydrated, and the metal is monovalent. So it's just sodium fluoride trihydrate. And the last one is, again, one that is multivalent. There's 1 copper bonded to 1 sulfate. Sulfate is -2, so that means the copper balancing with it must be +2. So copper 2 sulfate pentahydrate, the hydrate at the end of that. Okay? So those are some practices of how to name ionic compounds. Again, they're ionic because they start with a metal. They always start with a metal, with the exception of if they start with the polyatomic ion ammonium. If they start with the polyatomic ion ammonium, they are still ionic. Okay? Now, how do we write the formulas? Like I said, you have to balance the ion charges, adding subscripts to represent how many of each ion is needed to balance the ion charges. So let's say I had calcium sulfide. Calcium has an ion charge of 2+. Sulfide is just the sulfur ion. And sulfur being in group 16 has a 2 charge. These charges already balance, which means I only need 1 calcium with 1 sulfur, and that's it. They balance. I don't need multiples of them. Okay? So it's just CAS. And if you wanted to put the states, like I said, ionic compounds are always in their natural form solid. Okay, if we look at the next example, this is a multivalent metal. It's telling me what ion charge to use. It's telling me to use a 2+. And hydroxide is OH -1. So this is similar to that calcium hydroxide example we did before. If I have 2 positives, I need 2 negatives. Okay? So we need 2 hydroxides. And because hydroxide is a polyatomic ion, it needs to be in brackets with a 2 written after it. And again, the state would be solid. Okay? Another way of thinking of this is, again, my iron has a 2+. My hydroxide is -1, so I need 2 hydroxides. That's where this subscript 2 comes from, needing 2 hydroxides. Okay? And then the next one we have sodium chlorate. Sodium chlorate. This is a hydrated compound, and I always just ignore the hydrate part and just focus on the compound part to start. Sodium is Na, and it has a 1+ charge. Chlorate. This is not chloride. If it was chloride, it would be the chlorine ion. This is chlorate. That's the polyatomic ion of ClO3 with a -1 charge. Okay? I have a +1 and a -1, so they balance, meaning I only need 1 of each. The 3 goes with the chlorate. That's part of the chlorate. If I needed 3 chlorates, I'd put a brackets with 3. Okay? So there's only 1 chlorate there with 1 sodium. And then tetrahydrate. So I put a dot, 4 for tetra, and hydrate again being water. Okay? So NaClO3.4H2O. Again, hydrated compounds are still solid ionic compounds. Okay? So again, there's some to try. So you can pause the video and give them a try, and then see if you're getting the proper answer. Now, in order to do this, I'm always writing down for myself the form of these ions and their ion charges. Okay? Bromide being in group 17 is -1. Lithium is +1. So lithium bromide would just be 1 lithium and 1 bromide. Again, if you want, you can put the solid state. When you have a naming chart, the states aren't as important, but when you write a reaction, they are. Okay, so I'm just going to skip them for now because we're not writing reactions, we're just naming them. Next is sodium phosphate. Phosphate is a polyatomic ion, PO4 with a 3 negative charge. So I need 3 sodiums to balance the 3 plus with the 3 negative. So that would look like Na with a subscript 3, PO4, meaning there's 3 sodiums. The fact that there's no brackets around the PO4 means there's just one PO4. Remember, the 4 goes with the phosphate. That's part of the phosphate. Next, we have magnesium nitride. Magnesium is 2 plus, and nitride is nitrogen. Being in group 15 has a 3 negative charge. Now, to get these to balance, it's not quite as easy, right? I have a 2 and a 3. So you have to think of what's the first common thing we can get them to, which is 6. That would require 3 magnesiums and 2 nitride ions. So the formula would be Mg subscript 3, N subscript 2. Again, meaning 3 magnesiums and 2 nitride ions. Now here's that ammonium ion that can replace a metal, and you still have what's considered an ionic compound. Okay? Sulfate is SO4 2 minus, ammonium is NH4 1 plus. I need 2 ammoniums to get 2 positive to match with the 2 negative. Now because ammonium is polyatomic, it needs to be in brackets. So I put my NH4 in brackets with the 2 subscript, and then 1 SO4, so there's no brackets around that. So it's NH4 2 SO4. The fifth one is calcium, which is Ca2 plus, phosphate, which is PO4 3 minus. So we have another one where we're going to need to get them to the lowest common multiple. I think that's the right math word there. The lowest common multiple, which is 6. So I need 3 calciums and 2 phosphates. So I have a 3 after my calcium and my phosphate in brackets with a 2. And the last one, nickel with a 2 plus, bonded to sulfite. Be careful, sulfite and sulfate are 2 different things. And what if I told you you had sulfide? Sulfide would be the sulfur 2 minus. Sulfate is SO4 2 minus. Sulfite is SO3 2 minus. Okay? The sulfate and sulfite are polyatomic ions in the polyatomic ion chart, whereas sulfide is just the non-metal sulfur acting as an ion. These balance. So I'll put it up here properly. I just need 1 nickel with 1 sulfate, but it is hydrated, so I put a dot and then 7 H2O for heptahydrate. Okay, and I believe that is it for this lesson. The next lesson will review naming molecular compounds and acids. Thank you for watching this video.